So for the last time, good morning, good afternoon, good evening, good night to all of you. And thank you very much for staying with this lecture until the end. In order to honor your participation a bit, I put up the flags of all the countries which have participated here. And I have to apologize to the South African group because this is the old flag which you had up to 1994. I simply don't have the new flag anymore. And I especially have to excuse, send an excuse to Mr. Badawi because I don't have the flag of the United Emirates. This is the flag instead. This is the flag of Oman, which is at least on the same Arab peninsula. On the right, you see the table again of our favorite nearing of the last lectures. By the way, this design can also be obtained from the founder plane. These are actually two founder planes laid over each other in a very skillful way. And we can see that if we have, instead of a nearing, a near field, what would happen here? If you have a near field, then all the rows here would have each element exactly once, which means that we have just one block, which is the whole nearing, without zero, and to have just one block is not a very good block design, so it's useless. It's also useless if it happens to be a ring, because Erhard Eichinger has shown that a planar ring actually is a near field, and so we are back to the same case as before. Hence, for getting good block designs, you really need nearings, not more and not less. Another aspect is how difficult is it to check computationally that this yields a planar nearing. Now, if you think of the definition, then you have to find out which elements are equivalent, and then you have to solve all these equations xa equal to xb plus c, and to find out if there is exactly one solution. So it's computationally quite involved, and hence you work quite a while to check if this gives a planar nearing. However, there's another way to do this, and for that one needs a little more theory. And as people say, the most practical thing is a good theory, and we'll find that this comes through also in our case. Namely the following. If you have a planar nearing n, then you might take some a in n and form the mapping phi sub a, which goes from n to n, sending x into x times a. And from that you can see if you replace x by some x plus y, then you have just the correct distributive law at hand to show that this phi a is an endomorphism. And so this belongs to the endomorphisms of n plus. What happens if a is equivalent to 0? That means all x sub a are equivalent, are the same as x times 0, which is 0. And so you will see that phi sub a is just the 0 map. If a is not equivalent to 0, then we'll show that phi sub A happens to be apimorphism, to be surjective. And I forgot to add here n planar and finite. Most things are also true in the infinite case, but let's assume this for simplicity. In order to show that phi sub A is then surjective, we take some B in A, in N, excuse me, and we ask, is there some X in N such that phi sub A of X is equal to B? Now phi sub A of X is X times A, and we get the answer from planarity, and the answer is yes. If we look at a certain equation, and this equation is X sub A is equal to X sub 0 plus B. Since A is not equivalent to 0, this must have a unique solution. And we can easily see that so we have a unique solution, certainly a unique solution, which means that there is an X, even exactly one X, and this shows that the map phi sub A is actually an apimorphism, and since n is finite as well, it's automatically bijective, and so in this case, if A is not equivalent to 0, then phi sub A happens to be an automorphism of the additive group n plus. So well, so good. And this phi sub A has an extra property, namely the following. Suppose phi sub A maps some B into B. So in this case, B would be a fixed point of A, of phi sub A. What does this mean? This means that B times A is equal to B. And recall that we had this private identity is 1 sub A of A. And we had the two things that by definition 1 sub A times A has to be A. But we then learned that for all n times 1 sub A is equal to n. So this private left identity acts as a right identity in this nearing n. And if we use this, we can form the following equation, namely x times A is equal to x times 1A plus 0. And in here we do have two solutions. The first solution would be 0. 0 times A is 0 times 1A plus 0. Yes, that's true. But also B is a solution, because B times A is equal to B times 1A, because B times 1A is B, and B times A is also B, as we have seen here in our assumption. And so we have two solutions. which means that we cannot have and B and 0B are different, which means, oh, yeah, and B unequal to 0. I forgot that. Because if B is equal to 0, phi sub A of 0 must be 0, of course. So we have two solutions, 0 and B. And since all these equations have at least one solution, unless A is equivalent to 1 sub A, we have the latter. So we have A is equivalent to 1 sub A. And from that, we get immediately here. So we get for all x the following, that phi sub A of x which is x times A, must be the same as x times 1A, 1 sub A, since they are equivalent, and x times 1 times A is equal to x by this, what we recall. And so we see that phi sub A happens to be the identity map. Thus, we see that each phi sub A is either the zero map or the identity, or otherwise it has only the trivial fixed point p equal to 0. And so we say that the collection of all phi sub A, where A is not equivalent to 0, is a fixed point free automorphism group. Denote here. I omit the proof that all phi sub A's where A is unequal is not equivalent to 0. Actually forms a group. And this group, let's call it G, is then a fixed point free automorphism group on n plus. And so we have the interesting thing that two groups are at the same time on the playground, namely the additive group of n plus and the group of all phi sub A's under composition. This is a situation which is sometimes addressed as that we have a so-called Frobenius group, the pair of G and N and the fixed point free action of G on N. And it's interesting to see that the converse also holds. Suppose we have one group acting as a fixed point free automorphism group on another group, then one can construct a planar nearing out of this. So this is a real essential remark. And fetch and play prove that the order of G is a divisor of the order of the multiplicative semigroup of N. Now, why is this a real advantage to the thing we had before? If we would like to check if this gives a planar nearing, then we simply have to look at all the phi sub a's. Where are other phi sub a's? Phi sub a is x times a. So if we fix some a, like a equal to 1, all the images are listed here in this corresponding column. And here we see that phi sub a must be the identity map, which also happens for a equal to 3. And for the others, they should be automorphisms, and we see 2, 4, 6, 1, 3, 5. These are just all non-zero elements. Each one appears exactly once, and we have no fixed point. 1 is not mapped to 1, 2 is not mapped to 2, 3 not to 3, 4 not to 1, and so on. The same with 4 here. We again have all elements of the multiplicative semigroup and in a different position than 1, 2, 3, 4, 5, 6. And so it's nice because knowing this result means that we can simply have a look at the table and just by uh, checking this without computing anything, we know, or we can find out if this gives a planar nearing or not. Well, to tell the truth, if we get just such a multiplication table together with the addition, in this case, addition modular 7, then we still have to show that we have a nearing at 10. And for that, we have to prove the associativity law and one of the distributive laws. Now, that is, as you know, quite cumbersome because in order to check associativity, you have to check A times B times C is equal to A times B times C. And that for all elements here. So we have 7 elements altogether. And then we have 7 times 7 times 7 products here. Again, 7 times 7 times 7 products on the other hand. So we have twice of this amount. And then we always have to compare if the results are the same. Similar with the distributive law. One can reduce the work a little bit. One can reduce it to the case that B is a generator of this multiplicative semigroup. Okay, then, and if it happens for, if it's true for all generators, it's a little less work. There's an interesting other way to find out if this is true or not, and this is similar to the tests that they are now doing in Austria with school children. If they have the coronavirus in them, they give them something to rinse their mouth, then they spit into some bowl, and then all together into the same bowl, and then one simply tries to find out if there is the virus in this bowl or not. In most cases, it will be not, and so the whole group, the school class, is proven to be without the virus. And in this few cases, when they find a virus, they simply take this single class, school class, and make single tests then, which is much, much more economical and faster than checking every child with a complete test. Now the same can be done here. Well, the same, we don't spit on this blackboard or so, but there's a way to mix all these elements in this nearing. or in this group weight, we don't know if it's a nearing at all. And the way to mix it is to form the so-called group weight algebra. Over some field, usually one takes the field of rational numbers. Uh, it's called, yeah, okay, group weight algebra. It consists of all formal sums of all elements in this group weight. And this forms an algebra in the sense of that it's a marshal and a ring at the same time. And then you can, that mixes all these elements, and then you can find out very, very quickly if the multiplication is associative, and you can do a similar thing with the distributive law. So that ends the considerations of planar nearings and their use, because I was asked if this block designs, since they helped me to discover the reason for my disease, will also be good for healing it. No, that's unfortunately not true, because right now a defect in the genes cannot be healed, but it helps me to stay at least away from complete breakdowns, because I now know that I have to worry because the intake of potassium, and to favor a lot of salt. And so it does, I'm still usually very, very weak during the morning up to 12 or 1 o'clock. And then I will be again very, very tired in the later afternoon. So maybe in 3 or 4 hours, I will have to crawl again on the floor and on four legs. It's not nice, but one gets used to it, and it's I tell you, it's by far better than to walk on four legs than to be unable to move at all. And I have never found a dog who has complained uh, for running on four legs through all of his life, and so it cannot be that bad. Well, now we come to the last section. It's mounted here already on structure theory. It's a vast theory and a deep theory, and all we can do with this limited time is to stretch it a little bit, and to but we can get the main result in this lecture, and that has a lot of good consequences as well. So So we might start with the considerations that if you have a field, then usually the field uh, acts on vector spaces. In the usual way that some lambda in the field can be multiplied with the vectors of this vector space. In a more general setting, a ring acts on what's called modules. And so it's quite logical to say that a near-ring acts on, let's call it, near modules. or as they are often also called N groups, where N is the nearing. How is such a near module defined? Suppose that give you the name near module M. M must be an additive group, of course, and the action must fulfill this, that we have N times M, N1 plus N2 times M must always be N1 times M plus N2 times M. And of course, we do not require that N times M1 plus M2 can be distributed, so we leave it with the same distributive law. And we have the fact that N1 times N2 times M is the same as N1 times N2 times M. And so we get a very natural way to define this as an N group or a near module. And there's a very nice example for that. Yeah, that's a notation. In this case, when M is an N group, we write it in this way, because N acts on the left to the elements of M. So a nice example, as I mentioned, take a group G and take the nearing M of G, and the action is clear. A function from M of G acts on the group G simply by F times G is F of G. This example is, of course, very, very important in this theory, and we might take a look at this, that if we have an element F in M of G such that F is the zero map let's say that F of X is equal to 0 for all X in G, then we can say, of course, that this is just the zero function, and so we might look at this in a general setting to say, suppose we take all an N modulo M, and if we take the set of all N in M such that N times the X now is the same as 0 for all X in M, then we collect all elements which vanish, so to speak, on M, or which kill every element in M, and we call this the annihilator, and simply write N of this N modulo M. And quite often it can happen that this annihilator is equal to 0, as we had in this case of the G marshal, the M of G marshal G. If this happens that this is zero, the marshal is called faithful. Otherwise, we always can say that this is in fact an ideal in the near-ring N, the annihilator ideal. Now we have that's the most important definition in this context, and that's the thing following definition. This chocolate is very hot. Suppose we have an N group, and let's take G now because we will be in the group area pretty soon. We call this N group G to be a primitive. If it is faithful, and if G is very small in this sense, that is no subgroup H, proper subgroup H of G, and also it should not be zero, so H G should be a proper subgroup with the property that N sub naught times H is in H. If you consider the case of rings and ring marshals, one also has the concept of a primitive marshal, and one says that the ring marshal is primitive if it's faithful, and if this marshal doesn't have any proper sub-marshals. They are defined in this way that ring times H is in H. Here we have to have N sub naught instead of N, otherwise we would get very weak results because the presence of constant elements here make the whole thing very messy. We also say in this sense that that N is primitive on G, or not precisely on Ng. Now, if you go away from ring theory, there are various ways to define primitivity here, and it was the merit of Gerhard Betsch to find the real correct and useful definitions, and there are various types of primitivity around, so that this here is perhaps the most important one, which is called in the literature to primitivity, and we adopt this alone and say simply primitive. Some examples. Suppose we're in the variety of groups. We have a group G, and we take P of G. This is primitive on G if and only if, well, it's faithful anyhow as a function nearing, and suppose we have a subgroup H, a proper subgroup, which is closed with respect to all elements of M sub naught. P naught of G, we know, consists of all sums of inner automorphisms. So it's primitive if it's closed with respect to inner automorphisms. And this means simply that this G must be a simple group. It cannot have any proper normal subgroup. So if G is a simple group, and if we change the variety to the variety of commutative rings with identity, and take your ring R out of that, we can say that P of R for the normal functions on this ring R is primitive on, well, G would be now the additive group of R. If and only if, so what do we have here? Faithful is again clear, but what happens with subgroups which are closed with respect to all zero-symmetric polynomial functions? We know they just generate the ideal, as we have seen before. And so it means that it has no proper ideal. And so it simply means that R is a simple ring. But a simple ring, which is commutative and has an identity, is a field. So we can say this happens if and only if R is a field. You see that primitive nearings turn out to be prominent things, namely simple rings, simple groups, simple other things, and so they will play a major role. The major role is the following. It's the main result here is the main structure theorem, and since I need it later, I can now erase this for the last time. So the main structure theorem would be the following. I'd like to give this in three versions. The first one is the easiest version, the baby version. Which says that if n is primitive on G has an identity and is finite, and we know we need another concept, namely that capital phi of Ng, which consists of all elements phi in the automorphism group of G, such that phi of n times G is equal to n times phi of g, okay, for all n in n, for all g in capital G, that this is just the consists just of the identity. Then one can say that n is isomorphic to one of four possible things. One has to divide the cases if n sub naught is a ring, or if it's not. And here, if n is equal to n sub naught, or n unequal to n sub naught. Now, in the first case, what do we get? The first box means n is equal to n sub naught, n is a ring, and so we have simply the classical result of ring theory, Jacobson's density theorem, which says that we get the full endomorphism ring of G, and it turns out that G must be a vector space over a skew field, and one knows quite a lot from Jacobson and other followers. And if n is not the same as n sub naught, then we have to add constants, and we have to add all constants. In this case, we get m affine of G, all affine maps on G, again G a vector space, and so the affine maps are just the sums of linear maps plus a constant. Now this is not exciting because that was known already. The exciting part is in line 2. Suppose we have n equal to n sub naught, and this is not a ring, then we end up at a very well-known near-ring, namely m sub naught of G. And if n is unequal to n sub naught, we again have to add all constants, which means that we are in m of G. And so the example we had before, that we have studied the near marshal G over m of G, or m naught of G, is really a very important example, because this is the main classical case of the density theorem. And the first version of this density theorem was brought up by Helmut Wieland in the late 30s. But the real good thing about the proper definition of primitive marshals and so on was then done by Gerhard Betsch, and so we owe him the basis of this density theorem, and he proved everything. The proof is pretty long and is out of reach for us in this lecture, but it is perhaps the most important theorem we have on near-rings so far. Now, that was the first version, and we might ask what happens if we have, for instance, the an infinite nearing N. And there we have the, so if N is infinite, we get the version for adults. We simply replace this isomorphism here by the word distance. In what does density mean? It means, suppose we have two subnearings N, M in M of G. We say that N is dense in M if every function in M, all these nearings consist of functions, if every function in M can be simulated by N, and the function in N, which means can be interpolated by a function in N at arbitrarily many, but finitely many places. So we can say it in this way: for all subsets S of G as finite, and for all functions F in M, there's a function H in M in N now, such that H consists restricted to S is the same as F restricted to S. So it means if we choose finitely many points in G, we always can find for every function in M a function in N, which coincides with this function F at this subset S. So the next thing is, what happens, we have done this with the finite, what happens if this thing here is not the identity? Now, if phi of mg is not the identity, we have to replace m naught of g and m of g by something else, namely replace m naught of g by m sub s of g, where s is equal to phi of n times g, union with the zero map. Okay, the US is in trouble. There must be time for release. It better be like this. And what does ms of g mean? These are all functions f from g to g, such that f of s times g is s times f of g, where of course this runs for all small s in capital S and small g in capital G. So here we have this phi of NG, which turns out to be a group, by the way, even a fixed point free group again, and we have to add 0, and then we get what's called a centralizer nearing, or for some reason it's better to say a decentralizer nearing M sub S of G. And so we then have to replace M naught of G by MS of G. We can here perhaps M sub S of G, and by smaller M sub S of G plus M sub C of G. So you have to add all constants again in this case. And so you can get rid of these things. And if we write down this main density theorem in the full version, so this would then be the full-fledged version. It means let n be primitive on G. We still need one in this nearing, and there exists quite a work on the case when we do not have an identity. Sometimes we get an identity for free, but we don't need this thing anymore, and we don't need this condition anymore. And we can say then n is tens in one of these four cases corresponding to the facts if n sub naught is a ring or not, or if n is zero symmetric or not. Now, this looks impressive, and it is impressive because the basic building elements for nearing theory in some way are the primitive nearings. And the primitive nearings can be now completely characterized by this structure theorem. It's not only impressive, but it's also quite useful. So let's apply this to some situation and to find out what it gives to us in other situations. For that, we applications. We first take a look at the nearings E of G, A of G, I of G. These are the nearings which are generated by the endomorphisms, by the automorphisms, or by the inautomorphisms. Remember, in the first lecture we have seen that if G is not abelian, the endomorphisms do not form a ring in general, or in most cases, and the same with the automorphisms and inautomorphisms. So they consist of all sums or differences of these endomorphisms here. A of G consists of all sums of or differences of automorphisms, and the same for the inautomorphisms. These are examples of so-called distributively generated nearings, because they are generated by distributive elements, endomorphisms, and especially automorphisms or inner automorphisms. Since every distributive element multiplies with zero in both sides equal to zero, all of them are zero symmetric automatically, and they have special properties, more properties than the near-rings in general. What are the E of G or A of G or the I of G subgroups of G? These are those subgroups such that call it H, that E of G applied to H lies in H, in the same for the others. This means these subgroups which are closed under all inner automorphisms, these are called simply the simple subgroups. Those which are closed with respect to all automorphisms they are called the characteristic subgroups, and those which are closed with respect to all endomorphisms are the fully invariant subgroups. So one knows these subgroups. Then there's something, since if there are no simple subgroups, simple, normal subgroups. Excuse me. If there are no normal subgroups, then there are also no characteristic subgroups, and then there are all, in all cases, if there are no invariant, no characteristic, no normal subgroups, the group is simple. And if the group G is simple, then we would have the following, that this group phi of n times G must be equal to the identity, because of the following, where n is one of these three near-rings. Because if it would not be the identity, recall that I said that this is a fixed point free automorphism group. It means then that G has a non-trivial fixed point free automorphism, because otherwise G has a fixed point free automorphism, which is not the identity. This means, by theorem of Thomson, that G must be nilpotent, and G nilpotent and simple. So G is simple. It means that G is abelian. So it's abelian and simple. So it's a group of prime order simply. And if we avoid this, the abelian case, then we can stay with this thing here, which means that we are in the adult version of our structure theorem, and we can say the following. So we can say that E of G E of G is equal to M naught of G if and only if G is non-abelian and characteristically simple, which means it has no proper characteristic subgroups. Why? Because if G is non-abelian and is characteristically simple, it has no proper subgroups which are closed with respect to n sub naught in the general sense, which is equal to n here, because we have automatically zero-symmetric nearings. And so the main structure theorem is applicable. We have the identity map here. It's then primitive on G, and then it stands in oh, I forgot, finite, yeah. G finite, and the order of G should be greater than 2. And so we get not even density, but equality remember, this was M naught of G here in the general sense, and so we get this. We can do the same for A of G. This is M naught of G, G is non-abelian, and sorry, wrong, not characteristically simple, invariantly simple. And here now we have characteristically simple. And we can do the same thing for I of G equal to M naught of G if and only if N is non-abelian and simple. So we can now say that we have an interesting situation. We have the situation that we can get a nearing, especially in the third case, equal to M sub naught of G, that every map which preserves zero, every map from G to G is the sum or difference of inner automorphisms, if and only if G is one of the famous groups, the non-abelian simple groups, and this is quite remarkable. And I asked the big shots of simple group theory if they knew it, like Fate or Thompson, and none of them said they knew it. It was obviously it's unknown to the group theorists that exactly these famous groups, which are now characterized by a very, very complicated proof of many thousand pages, that every map from G to G is in fact the sum of inner automorphisms, and this is quite a deep theorem. The earliest version of this was already done by Fröhlich in the late 50s. And if you replace a finite by, if you cancel a finiteness, you see that we get density. So the inner or the I of G is dense in M sub naught of G in this case, which means that every map can be interpolated by a sum of inner automorphisms. Now, another point where we might perhaps apply this, or at least we can perhaps use this result, is the following. Put the following question. Suppose we have the situation that we want to find out if conversely every nearing can be embedded into a distributively generated nearing. Can every nearing n be embedded into some distributively generated nearing M? Now we can replace this by every nearing n can M sub naught of G. Here we have to have zero symmetric nearing n equal to n sub naught, because otherwise we're constants and we would not get the constants out anymore if we do these embeddings. Because if we can replace m naught of G or embed m naught of G into some dg nearing n, we can, since every nearing can be embedded into this, we can embed every zero symmetric nearing in the dg nearing n. Now the thing is that the answer is yes if G is finite. That's a result by Henry Heatherly. And in this case, it's done in the following way. First embed G into some full symmetric group. Every group can be embedded into a full permutation group. And S sub n can further be embedded into the alternating group on n plus 2 elements. That's not very hard to see. And so M of G can be embedded in M of n sub n plus 2. And this is a simple nearing. So M of n sub naught of G can be embedded into M sub naught of A sub n plus 2. And this is a simple group if n is at least 3. And since it's a simple group, we can say this is the same as I of G, and so we can embed this even into the inner automorphism group of A of n plus 2. And so we can embed it into E of n plus A of n plus 2. And so in the finite case, it's quite easy to see if n is not, or G is not finite, then we run into the trouble because then we cannot do this anymore to embed it into a simple group. And in this case, we have infinite simple groups, and they are a real horror in many ways. On the other hand, uh, there's some hope to have this, because John Meldrum showed that every excuse me, that the variety of zero-symmetric nearings coincides with the variety of generated by the distributively generated nearings, which means that every nearing can be regarded as a subnearing of of a homomorphic image of a type product of PG nearings. So there's some relation between the class of all zero-symmetric nearings and the class of PG nearings. But up to now, this question is open in the infinite case. In fact, I worked with Gary Birkenmeier for quite a while on this problem, to start with a nearing n, or let's take n naught of G, and to enlarge the group uh, uh, G in order to find a proper embedding into perhaps E of H, where H is greater than G. And this is turned out to be really difficult. If one can achieve this, well, E of H is a PG nearing, and so this question would be answered. And we're on a good way. We enlarge G tremendously by going to the free group over the elements of G, and this again to make it bigger and bigger and bigger, and then some amalgamated products, and finally this embedding map turned out just to be the zero map, the greatest disaster for embeddings. So this didn't have to do with the structure theorem, but maybe one can use this uh, in another sense to get an embedding of this type. So let me then close with another application. Would be the following. Suppose, take this result. Suppose n is a nearing, and this time it's not zero symmetric. And n the subnearing of M of G, sub G, containing the identity, map, and suppose that n sub naught is not a ring, then one can prove easily if n is, let's call it threefold transitive, on G, which means threefold transitive means one can interpolate that every every function on 3 points, or in another way, if we take G here and there, and if we fix 3 points, then we always can find the function f in n, which passes through these 3 points. So if this happens, then this is equivalent to saying that n is tens in M of G. Why? Because if n is threefold transitive, one can prove that this group phi of ng we had was trivial, consists of only the identity, and we have the identity there. So if we look at the main structure theorem, we have and then if this happens, n is also primitive on G, and so we have that n must be dense in, and now what box do we have? N is not n sub naught, and n sub naught is not a ring. So we are down here in this fourth box, and since S is trivial, this is m naught of G plus m constants of G, and so this is just m of G. So it's a direct consequence of the main structure theorem, and it can be rephrased in this way, that if we have these conditions here, and one can interpolate every function from G to G at 3 places, then it's dense, which means that we can interpolate at arbitrary many places. And there's some story behind this. I once went to a talk to Vienna of my former supervisor, Winfried Neubauer, and during the talk he raised the question, suppose we have an expanded group G, how what is the number n if there's any, so that n-fold transitivity implies density. And I was just thinking about these at those days. And so during the lecture, I could already answer this question. N must be 3. 2 is not enough. But if it's threefold transitive, then it's automatically 4, 5, 6, 7, and so on transitive. And this solved the problem in universal algebra. And it never was quite surprised that his open question had an answer which was easy to derive from Near-rings in this case, and from the main structure theorem. Well, that about ends the series of these talks, and I would like to thank all of you that you stayed until the end of this, and so I wish you all the best. I hope that these lectures will be in some way continued, maybe not by me, but by somebody else. I don't have to speak all the time. And so we can say that in this case, perhaps we'll find somebody who is giving lectures on similar topics, maybe already in this spring semester. And I spoke with Gerhard Betsch before this last lecture now, and he said he, at least he will think about this positively to get the whole thing continued. So again, thank you very much for attending, and I hope you uh, have a good time now, and I hope you stay away from the virus. So keep well, and all the best to you, and thank you very much again. Bye bye.